Video.
Are we recording this as well?
This is recording. This has been recording for half an hour. Hope you said
nice.
some cool. No, I had the audio off. Hopefully, I don't know. I can't promise that.
Yeah, that's fine.
I don't know. Like, I wouldn't talk about a bunch of like really heavy political stuff.
No.
How do we look on there?
Are both in the screen, but Brady, you're a little maybe too far to the left.
All right.
Yeah,
Okay.
now you're
All right, guys. Good
Wait.
team effort over here. I can just turn my mic. We're gonna get this worked out one of these days.
One of these days.
We're gonna figure it out. All right, guys. Everybody, welcome to the swamp. We got a big turnout today. Thanks for everybody coming down during what is this, tropical storm Haley or something?
Began with an H. Helene?
Helene.
Was it Helene?
Helen. Yeah, we got a great turnout. I think we got some people online.
It's literally a swamp today.
It's literally a swamp. We've got things leaking. If you're on the YouTube, smash that like button, subscribe. You're just like, I have to say it because we're on YouTube. I think that's like a law.
Yeah.
But we've got great presentation today. I don't have any announcements for up front. Just glad everybody's here, so we'll kick right into it. Today, we're going to talk about a practical guide to web audio APIs, brought to us by Brady O'Leary, who's a frequent Silicon Swamp person.
Yep. I'm a swamp person.
Swamper, Swamp-E, Swamp-et, I don't know. We hope everybody's having a good time. The people that aren't here, you're staying dry. Feel free, if you've got questions during the presentation, to throw them up on YouTube, in the YouTube chat or in the Discord, and we'll do our best to feed them out to Brady.
Cool.
Now we're going to do our, as per tradition, we're going to do our awkward interview section of the evening.
Yeah.
Brady, thank you for coming. Thank you for being here with us today.
Great to be here.
Yeah, I appreciate you braving the storm.
Absolutely, yeah. I mean, my car almost washed away on the drive over.
So, Brady, tell me a little bit, for those who don't know, tell us a little bit about what you're up to now, what you do for work.
Yeah, so, I work for a company that does, rewards platform for a lot of gas stations. So we integrate directly to the point of sale systems. So if you've ever punched your phone number into a gas pump, there's a high likelihood you've interacted with stuff that I've worked on. But basically, we consume the phone number, list of items that you bought, and based on whatever our clients want, right? We can give them offers based on that. So.
All right. And how did you your role in this company is as CEO?
I wish. I wish. No, I'm a back-end Node engineer. So
you mostly work with Node. How did you get into tech? How did you get into software?
Well, I've always been interested in computers to the point where when I was younger, people would be like, "Oh, you're interested in computers? Oh gosh, I've got this old one up in my attic." And so I was that kid, right? So but learned more about programming in high school. Taught myself how to write little basic programs on my TI-84 calculator to the point where it slowed down a lot. I've never seen other calculators do that, but I programmed the crap out of that thing. But then I learned took Java in high school and did my CS degree at Carolina. So.
And are you a local here to the Midlands?
I grew up in Aiken, but I have lived here in Columbia.
That's basically Georgia, bro. No, that's cool. So you're a USC graduate, local to the Carolinas.
Yeah.
Because I think it'd be cool you've got a cool. I have gotten to preview bits of the presentation, so I'm actually just excited for this because it's very visceral. You have some cool stuff for us. I'll ask my famous last question, which is is there anything in tech right now that you're kind of excited about, whether software or not, but just stuff that you think is cool?
I think all of the development around large language models and neural networks, everything that people calls AI, but with my computer science background, I don't really like to call it AI because that's too general. But I think that's really interesting, and I'm really excited to see where it goes, even if it puts me out of a job in the future.
I hope it doesn't put anybody
I hope
out
it doesn't. I don't think it will.
I don't think it
will.
Either.
We're a way off.
As an AI
it'll make
guy.
us a lot of it'll make us all a lot more efficient and really take the grunt work away, I think.
Oh no, I think there's a cool opportunity to make work not suck so much.
Yeah, absolutely.
I think the biggest problem we have right now with AI is that all the AI we focused on is doing our writing and our painting and our art for us. Which is all the stuff that we wish we could be doing instead of work.
Yeah.
And we need to focus more on getting it to do work for us so that we can paint stuff, code weird things, make music. All right, I'm gonna let you dive into it. Give me a second to flip over the camera.
Cool.
I'm also gonna see if I can figure out how to get the air on a little bit for you. It's a little warm, but Just in case you're wondering about that. I know it's
Okay. Yep. Let me go ahead and.
I'm gonna place this secondary microphone here,
Sure.
so hopefully we'll get the audio out. Looks like that's working.
It should be.
I've got your slides. I just need to make the camera smaller so that you're just in the corner.
Can it see me where I'm standing?
It will when I move it.
Okay.
Because it's a lot easier because I know you don't want to stand right in front.
Yeah, I don't want to be blinded by the projector.
No. Oh, we can't say that. We'll get kicked off.
Yeah, we'll get a copyright strike.
Yeah. Actually, if we get one for that, that'll be like an achievement.
Yeah, really.
Okay, the only thing I'm having trouble is, are you presenting something? Yeah.
Yeah, should be. Is it showing up on your side?
It's not showing up on my side. It's okay. It's okay. So let me try one more thing. There it is. Got it.
You got it? Okay.
You are, my man, you are live.
All right.
Tell the world all about web audio.
We're going to learn some things about WebAudio APIs today. So today I'm giving an overview on web APIs and a practical way to use them. But in swamp tradition, we're going to introduce our swamp animal of the evening. This is an alligator snapping turtle. It is the one that is at the Ruth Patrick Science and Education Center at USC-Aiken. Saw it when I went there for a planetarium show a couple weeks ago. But anyway, so let's talk a little bit about the history. Let's talk a little bit about the history inside, about like audio inside of a web browser. So the original web browser that Tim Berners-Lee wrote did not include any audio support. That was back in 1990, but as time went on, of course, that was a desired feature. So we eventually supported embeds, and Flash ended up being the most common way of playing back audio right up until the HTML5 spec came out, which included both audio and video tags in the early 2010s. Around the same time, Mozilla actually proposed an audio data API, but then dropped it in favor of endorsing what became the WebAudio API that we know today, which was the first draft of which was introduced in 2011 by the Audio Working Group, which was composed of industry engineers from companies including Google and Mozilla. Firefox was the first browser that I could find to fully implement this in late 2013. Chrome fully implemented this in 2014, and the spec was fully ratified in 2021. So let's talk about sound. First thing I want to talk about is A440. Bear with me, let me get my mouse over here. That is A440. What's the significance, may you ask? It is the A above middle C and is a standard tuning frequency. It in fact has been assigned the standard ISO 16. It was formalized in 1975, but has been an informal standard since the 1920s. Before that, some places in Europe were using 435 hertz for their A. There were a couple of other ones as well. The second thing I want to talk about is how we mix audio together. This screenshot right here was taken from Audacity, where I generated two different sine waves, one of which at 440 hertz, the one below it at the other frequency. They sound a perfect fourth apart, so you have your A and your D. And then this third column right here, or this third row right here, you can see where they are mixed together, so you can see how we're basically just adding all of those points together. And so you get both waveforms. They make some of the peaks a little taller, some of the troughs a little deeper, sometimes shallower. There's some destructive interference there. One thing I do want to mention while we're here is that if a signal is too hot, it'll lead to a type of distortion that is called peaking, and that is where the waveform actually goes outside of and gets clipped, and leads to a very kind of harsh sound. Next thing we need to talk about is the sample rate. And basically, samples are points of sound. We're looking at discrete samples from a continuous waveform. That's how computers process sound. Two common Two common sampling rates are 44.1 kilohertz, which is known as CD quality, and 48 kilohertz, which is known as DVD quality. And there is a theorem that I want to talk about as well. So the Nyquist-Shannon sampling theorem states that the sample rate must be twice the signal bandwidth to avoid aliasing. And that basically means that if we want to represent a signal at, say 440 hertz, we need to have a sampling rate of at least 880 hertz to be able to reproduce that frequency in the first place. Now, it'll be very distorted if you do that, but keep that in mind. In that mismatching sample rates can sometimes lead to artifacts during playback, or even playback at the wrong speed in some software. And you can think of it as like resizing an image. But you may ask, why 44.1 kilohertz? Well, that's because the range of human hearing is between roughly 20 hertz to 20 kilohertz. And given that Nyquist-Shannon sampling theorem I talked about earlier, we need more than 40,000 samples to be able to accurately reproduce sounds within that range. Signals are usually then filtered with a low-pass filter to kind of cut off some of those higher, harsher frequencies, just to reduce artifacts being reproduced into the audio stream. So next thing, we'll go to the WebAudio API basics. We'll talk about the paradigms of the API. And really, it's pretty simple. Like, we're just taking nodes and connecting them together. It's really like plugging, different pieces of audio equipment into each other. And the other thing is that, there are ways to schedule start and stop times for nodes making sound, as well as to set the value at a particular time with audio parameters. So those nodes have parameters that you can set. So you remember that A440 example I showed you earlier? This is the code that generated it. Like I said, it's conceptually pretty simple. We're plugging an oscillator into a main output. But this audio context right here is your gateway into the WebAudio API. You need it to be able to create nodes, and it's essentially the thing that encapsulates all of that. This is a graphical representation of what we built earlier. We're just taking the oscillator node and plugging it into the audio context destination. That's like the master output, basically. But yeah, so let's talk about audio parameters. They're exactly what it says on the tin, right? It allows changing a value with respect to time, and that is why it's not just a value on the node class itself, is because we want to have the ability to set the value over time. And you can also just change the value directly, but once you set a value like at a given time, it ignores that. So there are two different types of audio parameters. You have your A rate parameters, which the current parameter value is used for each sample frame, and you have K rate parameters, which use the same initial audio parameter value for the whole block process. That's 128 sample frames. You can see here, I have two code examples of setting values on a parameter. So I'm setting the frequency of the oscillator here to 880 at the current, or quarter of a second ahead of the current time. And by the way, the audio context current time is actually represented in seconds using a very high resolution floating point number. And then down here, we're just directly setting the value to 880. Yes?
What is a sample frame?
The sample frame?
Yeah. It says like it's for 128 sample frames. What does that mean?
A sample frame, I believe, is just like a collection of samples. I don't remember how many exactly are in a sample frame.
So it's just like a very short snippet of the overall.
Yeah, think of it as like a short snippet of the waveform, basically.
Makes sense.
But yeah, so here I have one of our other demos. This is setting a value at quarter of a second ahead of the current time. It sounds like this. And basically, what we're doing here is it sets the value based on the initial parameter that's put in. So like it's beginning to change to the new frequency at the time specified for the previous event, and that's when like the previous event sound was started. So that's actually more relevant for this, where we're linearly ramping to 880, and you'll hear that it actually starts doing that immediately because the last event was setting the initial value to 440. So that's why it sounds like that.
Remember when we were worried that this was going to be loud?
Yeah, this is pretty loud.
I don't know how it sounds like.
Yeah, I hope I'm not like blowing people's. I hope I'm not like blowing people's eardrums out or anything.
We have 5 people watching. So
Okay, cool. All right. So another interesting thing is that you can actually connect the output of audio nodes directly to audio parameters. And this allows for continuously changing a parameter value. But note that you cannot go the other way around. It doesn't really make sense to you anyway. So what I'm doing here is, creating the audio context, creating a regular oscillator, then creating another oscillator that I'm using, as a low frequency oscillator. You can see I'm setting its frequency value to 4. Connecting the oscillator to the gain node, connecting my gain node to the, audio context destination, connecting my low frequency oscillator to the gain control on the gain node, and then starting all the nodes and scheduling the stop time. So that's why it sounds like that. You can kind of hear the wavy sound. Yeah. Yes.
So the low frequency node is adjusting essentially the volume of the oscillator.
Exactly.
The rate at which the volume is being changed is the 4 hertz from LFO frequency.
Exactly, yes. Basically, what I just told Charles is that the low frequency oscillator, moving at 4 hertz is directly adjusting the volume of the other oscillator. All right, let's move on to scheduling. So this is the last important part of the API paradigm. Audio scheduled source nodes allow setting start and stop times for when the node starts and stops playing sound. And audio parameters have like 7 different methods for setting values at a given time, as well as interpolation between the current and target values for some of those options. That interface that I just told you about is implemented by that oscillator node. There's another constant source node and the audio buffer source node that we'll later use to play some samples. Yeah, let's move on. So how do we actually generate sound? Well, we've been doing this a bit already, but you can do that with 5 audio and video tags, which you can actually convert into audio nodes. Now, of course, it's built so that you don't have to do any special JavaScript, to be able to like embed an audio like file into your web page. But what's cool about this is that I can do that and then also, connect it to like a gain node or some other effects and stuff like that. Basically use it like I would any of these other audio nodes we've just been looking at.
The feedback we've gotten for your current sounds is, I thought the first noise was a flood alert.
Oh, well, I did get one of those earlier today too. So, anyway, so another way to generate sound is by using an oscillator node, which we've done already. But there are a couple of different types of sound waves it supports. So get ready for another flood alert. So you have a sine wave, a square wave, which you can see that the waveform looked more kind of in a vaguely square shape. Sawtooth will look kind of like a sawtooth shape. And then you have the triangle. So if you're familiar with like a lot of older video game consoles, a lot of them used square, triangle, and sawtooth waves to generate their sound. Oscillator nodes can also use a custom waveform type. And actually, what's really interesting about this is that it uses an array of floats to perform an inverse Fourier transform to generate the sound. So this, for instance, right here would just generate like a regular sine wave. But I've seen some code online that generates really complex sounds with that using a periodic wave. So let's move on to the audio buffer source node. So now we're going to get into sound sampling. So here we're loading an audio file into a buffer and playing it. We can change the pitch by using the krate detune parameter. And you'll see that it's measured in cents. Cents are basically a division of a semitone. A semitone is like a division of an octave. You have 12 semitones in an octave. You have 100 cents in a semitone. So basically, I can play this sound, and it's just a crow. And I can also play it at a perfect fourth below. So it plays back slower, has a lower pitch. Now you'll notice I used this very convenient function right here called load audio file to actually load the audio file. So let's go take a look at that. So what we're doing here is basically fetching the audio file that I put into it, decoding the audio data from the array buffer response that we get back from actually fetching it. And basically, I think all this does is it loads it into the audio context and provides a way for it to generate new playback nodes. One thing worth mentioning too is that these audio buffer source nodes, as well as those oscillator nodes, you can't reuse them when you stop playback. So think of them as disposable, basically. So like when I'm clicking this button, it's like, making a new node, but you don't have to reload like the audio file into it because you have like a reference to this audio data inside of your audio context. It's actually a very low cost operation to repeatedly play back sampled sounds. But yeah, so let's move on to the last big way that we can make sounds, and that's using an audio worklet. Basically, it's a special type of web worker, which is like a separate thread in a web browser environment that can generate audio directly into a buffer. And so, here, I did have to add a gain node for the same reason that I said earlier, where you can't really reuse nodes. But the thing about the audio worklet node is that it's like a continuously continuously generating sounds. So like, can't really stop it. So this is the actual worker code. I just pulled this off of Mozilla's website. It's generating white noise using random values and putting them into the output array. And it sounds like this. This might be a little loud. So you get your white noise. But yeah, so let's move on to effects. These are all the different types of nodes that you can use to alter sounds. And I'm going to demo this using an audio loop. So I'll go ahead and start playback. So I've got a fun little song here. Let's look at the bicloud filter node. So what's nice about the filter is that you can essentially get rid of a bunch of frequencies you don't need. And all I've done here is these are all like audio parameters on the bicloud filter node. And behind the scenes, I have the inputs hooked up to actually change the values on that. So I can, move the frequency slider around. You hear that I get, we're actually looking at a low pass filter right now, but I can get rid of, some of those sounds. This Q parameter here is short for quality. It basically changes like the way that it filters. So like you can see when I add that back, it has like kind of a harsher sound, right? You can also see this little dip right here that follows the frequency. So yeah, let's look at a high pass filter next. So this does the opposite of a low pass filter and gets rid of all of the lower frequencies. The Q works in exactly the same way. This doesn't want to work, but yeah, you can hear it, moving up and down. Let's move to another type of filter. So this is a bandpass filter, and basically what it does is that it allows a narrow range of sounds to go through. Basically a band, if you think about it. This quality value adjusts like how big that range is. So if I crank it like all the way up, and that's actually not as far as that Q value goes. I limited it here in the examples so I don't, accidentally blow anyone's eardrums or speakers out. You can get some very harsh sounds out of it. But you can see where it's like showing a narrow range of frequencies. This gain audio parameter doesn't actually do anything for a lot for those first 3 types of filters. But if we go to the low shelf, it's kind of like low pass, except that this gain, I think, determines like how the sound is like attenuated. So if I turn it like all the way up, yeah, you can hear, you can get some distortion out of this very easily. So we go to the high shelf, it does the exact opposite thing. So like if we do that, you can hear it change. Peaking is kind of like the band pass that we saw earlier, except that it also utilizes gain. So the notch works exactly the opposite way of the bandpass filter, so you can see that notch where the frequencies are, increased. And then the all-pass filter basically lets all the sound through, but it readjusts the way that it changes the phase relationship between all of those frequencies. So let's move to reverb. This uses convolution reverb, which sounds like this. It's like you're playing, music in a gym, basically, where the sound continuously reflects and, reverberates. And the way that this works is that basically we're loading in a audio sample to use as our impulse, and we combine it essentially with the existing audio. I think it works. I think it uses like an inverse Fourier transform or something like that, basically determining like what frequencies are allowed to like continue in the sound and reverberate, I guess, to make that type of sound that we hear. But basically an impulse waveform just captures the acoustic characteristics of a location. So the delay node does exactly what it says on the tin. It introduces a delay into the audio, which could be interesting if you're trying to maybe create like, certain types of effects. So the last one that we're going to talk about is the dynamic, the compressor module. So basically what this does is it compresses the audio. It like automatically ducks the volume if it goes past a certain threshold. The ratio determines like how much it compresses the audio, and the knee, I think, is the initial amount. Attack and release are just times, so you can kind of do some fun things like but yeah, so we're going to stop playback of that. Gain nodes, we already saw a bunch of those, so I'm not going to demo that again. It's basically just volume. Really not that interesting. So let's talk about audio analysis. How do we analyze audio? Well, we use this great thing called a Fourier transform, and it's used to get the frequencies out of a waveform. And this can also go the opposite way through something called an inverse Fourier transform, but we're very lucky because the WebAudio APIs have implemented this for us. So we don't have to do any of that math or implement this at all. And it does that using an analyzer node. We saw this earlier, and actually we saw this earlier where we had the bicolor filter. This is actually the output, the Fourier output, so we could see like the actual frequencies of the audio. And then the other example of this, it draws it to a canvas. The other example that we saw earlier was here, where we had the sound waves, where it would draw the actual waveform. But yeah, so if you remember that custom waveform type I talked about earlier with the oscillator node, like I said, that implements the inverse Fourier transform to generate the waveform from those frequencies. But yeah, so I threw a lot of information at y'all. Any questions or comments or anything?
So one thing that I think is kind of interesting is how would you handle audio breakout? Okay. No, that's fair. I forgot how microphones work.
Right.
Yeah. So suppose that I wanted to create a website where I had an infinite remote audio source, and I wanted to have continual playback until t equals infinity without running out of memory. Right. The approaches you've shown, you load the whole file all at once. But is there also a way, maybe the audio worklet thing, where you could like stream in chunks of audio and then stuff it into the audio subsystem, continually, so that way your memory usage is constant, forever.
Right. I think there are actually two ways to do that. So the audio worklet could probably be utilized for that. And then I think there's also another node you can use to actually basically do the same thing that you do with the worker that I showed earlier, but it's not being done inside of a web worker. It's being done like synchronously inside of your main thread. But that should be possible. I don't actually know off the top of my head how you would do that.
Yeah, I mean that's a little more advanced than a demo, right? Like,
yeah,
there's probably not that many people with that use case. Internet radio, I guess.
I mean, things like YouTube, major video providing websites very likely do this, as well as audio streaming, right? Because it really doesn't make sense to like load chunks of audio that you're never going to play again. So I would imagine in a case like that, you would have a set buffer size, and essentially write to that buffer and have your playhead basically right behind it, playing those audio samples, continuously behind where you're writing them, and hoping that you never overlap. But that way, it stays confined to like a single area of memory.
Another interesting thing I noticed is that it seems like this audio subsystem has its own special time handling. I'm assuming that's how they're getting around the problem of your web browser is not a real-time application running on a real-time kernel, right?
Yes.
So you can kind of do everything in the background and then send it all to the OS, at once, or at least one big chunk at once.
Yeah, that's exactly how that works. I don't know if I mentioned it earlier, but all of the audio processing happens behind the scenes for the most part. And this is really just controlling, like, it works exactly like that. There's a separate thread that handles all the actual audio generation and sending it to the operating system.
Which I guess also means a slow foreground thread can't really screw up your
exactly.
audio playback, once it's all configured and started.
And to be clear, right, this is especially important in a web browser, because the way that it works is that you have one main thread that's shared between actually rendering your web page and running all of the JavaScript inside of it. So if you had if you had to do that synchronously, you'd end up with a lot of pops and artifacts inside of your sound that would not be desirable. You have a question? Okay. Okay, well, let's move on. Yes.
For application-wise for this, right? Like you've shown, most of the examples you've shown have been like generated sound, where it's like, oh, like a MIDI, like, generate these sine waves. But I would suspect, is that like the typical use case for this? Or I did see that, I think at one point you played like a little FLAC sound. Or is it more likely that you have like little bits of snippets recorded that you're just feeding up?
I think most, I'm actually not sure, but I would assume that most likely people, developers are probably playing sounds back. They probably have groups of samples that they're, playing back. If it's like a rich multimedia application, that's probably what's happening, is that like, they've had their artists go make all their, music. Maybe they get like one track, maybe they get a couple tracks. If you're making a really basic game, like, you're probably going to be playing all samples back, unless you want to be special and use an oscillator or something like that.
And is this API? I mean, I know that it's currently used, but is this like an old API that's been around a long time, or are you showing us something that's like how long have I been able to do this relatively?
So
with this framework.
Yeah, it was fully ratified in 2021. But this API has been around since like the early to mid 2010s. So not really what I would consider old. in the scope of a web browser.
Because I was getting some real GeoCities vibe, like
Yeah.
like if I was
No,
putting together
like
an
this would
Angel
be like the
Fire
exact kind of
site.
thing that you'd want to like put on. There's actually something called NeoCities, which is kind of like the old GeoCities.
Yeah.
Um,
Yeah, I didn't realize that it was this new.
Yeah.
Yeah.
It was like, I wonder how we did it before. Now I'm kind of
Well,
curious.
I guess Flash Player, like the old API one, was actually running native object code.
It
I
was.
assume it was just using an OS syscall to
Yeah.
use
It would have had
just
to.
essentially rolling its own audio driver, basically.
right.
Okay.
Well, cool. Let's talk about MIDI. So, the important thing to remember about MIDI is that it does not carry audio data. It only triggers sounds, and it's basically like a glorified serial protocol. We're only going to touch the surface of MIDI. We're not going to go too deep into it. I'm going to cover note on and note off commands, but basically those show up as 3 bytes, I guess, and you get the first byte is both your channel and your status. So it'll send a value from 0 to 15 for your channel, and then the second byte is actually the status to say like note on, note off, control change, other stuff like that. For the note on and note off, your second 2 bytes are going to be what key you pushed, and the third group of bytes is going to be your velocity or like the volume, basically how hard you played that note. We can take a look at this in Linux earlier, look at the command line, but I might skip that for now. So that's what I just talked about. One important thing to note is that sometimes note off messages are sent as a note on message with a velocity of 0, which is a little annoying, but we can work with that. How do we convert from MIDI notes to frequencies? So MIDI has a range, its note range is basically 0 to 127, and middle A is, or A440 is MIDI note 69. Nice. But using our normal tuning system of equal temperament, we can actually use oh dear, that broke. So using our tuning system of equal temperament, we can actually calculate the frequency. One important thing to consider about equal temperament is that it's actually kind of a compromise of older tuning systems. So it's not perfect, and it was initially developed around the time that the piano was invented because, well, you can play in any key and you need all the notes to sound good together. So this is an example function I wrote inside of one of my projects where I'm actually getting, I'm feeding in the note number and getting back the actual frequency. Basically, I'm taking the power of my equal temperament constant, which is 2 to the 1/12th, and then using my reference note and the reference pitch, I can figure out what its frequency is. Yes?
See perfectly, G would be way off.
Right.
So you don't have that problem. So why use equal temperament here? Use to it.
Mainly because we're used to it, and it's a lot easier than trying to calculate. I mean, really, the equations. There is an equation to do that. This is readily accessible. That's why I picked it. Yes, and really that's where MIDI got its start was, electronic pianos and synthesizers, and sending commands to, play them from, either a computer or like, some kind of MIDI controller. Yeah, let me get out of this and go backwards. So in order to use MIDI inside of a web browser, we first need to get permission. And to do that, I'm going to show you another code example from the same project where first you would call this prompt function, which essentially queries the, and by the way, this is all written in TypeScript. That's why you see like all of these types here. For those of you who don't know, TypeScript is basically JavaScript with types, and it makes it for the most part, a lot more convenient to work in. But basically, we're querying to see if we have permission to do MIDI. And then when we actually start, this is when we get our MIDI access, and you know, that's our actual MIDI access object. From that, we can get you know, all of our you know, MIDI inputs and outputs. I'm going to be able to show you that shortly, I think. Or no. Well, we're going to go back into this and go. Bear with me a sec. So if you go to MIDI and nodes, we can see an example of the MIDI input node. The output node works in a very similar way, but this MIDI access right here, if you follow it, here we're getting all of our inputs, or all of our like MIDI input devices, setting them into a map so that it's convenient to use later inside of our project, and then listening for state changes on those MIDI events. This is, or actually on the MIDI access object itself. And this is how we are able to determine if MIDI devices are connected or disconnected while we're running, you know, MIDI in the browser, so that we can, you know, properly accommodate that. Handling the MIDI message is the other big thing. So basically what we're doing here is, wait, I think this is, oh, no, I'm sorry, this is what I was looking for. So right here, we're building the actual MIDI port. This is where, and this MIDI port is from, you know, that group of ports that we were looking at earlier, those inputs. And basically, we're listening for events on that. Whenever you play a note or, you know, stop playing a note on any device, you get events to handle. And from that, you can determine like what notes were pressed, you know, properties of that note, stuff like that. I'll go back here.
This is a lot closer to an API for handling keystrokes than like audio. Like it's not synthesizing the actual sounds.
Right, not yet.
I mean, your command isn't what it is, right? I mean, because it gets the velocity and stuff.
Right, so we're just sending commands around, like serial, like, you know, bytes and whatnot, to like say that, hey, I pushed a note. And then whatever happens on the other end is, you know, an implementation detail. The second thing I want to show is how we can build a sequencer using the WebAudio APIs. And so in this example from the same project, we'll go down here. So you're going to see all these things about like music engine oscillator nodes and audio ports. Those are abstractions I built on top of the WebAudio API to basically make a polyphonic synthesizer using that oscillator node we looked at earlier. And this audio port, the port abstraction is really just a way that we can connect nodes together, so that it's kind of like those audio parameters really, but, you know, I can have different types of ports and, you know, send data where it needs to go, connect things together really easy. So basically what we're doing here, this function generates a repeating sequence of times to say like, it basically gives us a tempo. So it'll generate times at, you know, 120 beats per minute basically. Forever until we tell that generator to stop generating. And if you remember what I said earlier about how, you know, the browser environment works, right? We can't have a thread that constantly takes up a lot of time, otherwise, you know, your page stops working. So we're getting around that here by using a set interval to periodically schedule the notes in batches. This is the actual array of notes. This is the sequence we're playing. It's, you know, the first 5 notes of the A major scale. This is the like look ahead number of beats, the time that we call the set interval, and that's in milliseconds. Oh, the other thing too that I want to call out now that I'm thinking about that is the MIDI API works entirely on milliseconds and not seconds like the WebAudio API does. So you have to convert between the two when you're scheduling. But basically all we're doing here is getting the next note, looking at the array of notes, and using this MIDI out port abstraction that I built to send like a virtualized MIDI note on message. So I have my key and my velocity, and then I have a time at which that's going to happen. And the reason I need that time is because I'm running this completely separate of that audio thread, and I'm basically telling the audio thread when to sound the notes. And so those virtual MIDI notes are going into that polyphonic oscillator that we saw earlier. And then I'm also scheduling a note off message so that the note stops playing. And what that sounds like, I can go ahead and show you that here. This is that code. Let me make this bigger so you all can actually see it. So this should play. So it sounds like that. So it would just keep repeating forever, basically. And that's the important thing about that type of sequencer, is that that's capable of going forever. And you can leave it running, right? You're not just saying like, I'm going to schedule all the notes for like the next 3 minutes and something like that, right? So the other thing that I want to show is that actually before that, we're going to bring over a software synthesizer. There is, you can actually send MIDI notes out. I'm going to go ahead and mute this and run that again. And yeah, okay, it disconnected. So I just had to connect that synthesizer again, and there we go. You can hear that it's making noise. So I have my web page driving a completely separate software synthesizer. I'm going to refresh this real quick. And one other cool thing I can do too is actually take MIDI input from a real MIDI keyboard and have it play back notes inside of this web page. So I'm going to click that to get that started.
Hold up the keyboard again. I think you there we go.
It's a Arteria Microlab controller, but basically, something's broken. Oh, I forgot to unmute the site. Silly me. So there you go. There's my horrible piano playing for the evening. But yeah, so let me go back over here, and we are just about to the end. So that's a sequencer that's taking MIDI input. Handling complexity, I kind of started to touch on this, but basically what you can do is you can encapsulate a collection of those basic audio nodes that you're interacting with in the Web MIDI API into these containers, and with the port abstraction that I built, that allows me to actually connect these like separate modules together and have them work in a very uniform way, so that like, if I supply the code for the polyphonic synthesizer, someone else could come in with like a sequencer that has a MIDI output on it, and I can feed that into my polyphonic synthesizer and have it actually work, right? My implementation is not dependent on anyone else's implementation, and that's the issue you would run into otherwise, is that like disconnecting and connecting nodes requires keeping track of like what nodes are connected. If you're trying to build a polyphonic synthesizer, actually I think this is the code for that. Yeah, this is the code for that synthesizer I was just talking about. So you can see I have abstractions for, where's that MIDI port? Oh yeah, that MIDI port's actually in the parent class, but it basically calls note on when you have a note turning on. So you can see that like I'm making a new oscillator node, I'm pushing it into like a list of active notes, getting the frequency, setting the frequency, setting its start time, and adding a listener for the ended event, which allows me to basically clean up. And disconnecting it so that the JavaScript, the browser can properly garbage collect it. And for note off timings, I'm just stopping the node and removing it from the scheduling map. And when that happens, when the note stops playing, this ended event gets fired. And so that allows for me to properly clean everything up. And I think we're getting close to the end. I'm working towards building another iteration of this. You can actually just go to my website and look up bork.deadcomputersociety.com. You want to do this on a desktop or laptop. It doesn't really work well on mobile, but basically you have a bunch of nodes you can connect together and play a music sample, see it visualized, and yeah. So some other audio libraries that you can use if you're interested in getting into the WebAudio APIs, but maybe don't want to like get your hands really dirty or just want to get something working quickly. Tone.js is a very popular option that a number of projects use. And Tonal.js is another library that I want to call out because it's actually a music theory library. So it's basically a collection of data that does the frequency calculations that I already wrote the code for, and also can tell you what notes are in a major chord, what notes are in a minor chord, what notes are in a scale, and things like that. There's a bunch of resources. I'm going to eventually post this slideshow up somewhere so that y'all can see it. But yeah, anyone else have any questions?
Bueller, internet, nothing.
All right. Well, thank you all for having me. I've really enjoyed the opportunity to be able to talk about WebAudio APIs for the evening and show off some stuff I've been working on. So,
dude, man, that was cool of you. I'm glad you could make it. Big round of applause for. I'll just make a couple of announcements and then we'll call it a night. Let me just put the camera back into full screen mode.
oh hey, it's Carl, just in time.
Our producer is here.
Just in time.
Let me just
close that again.
Turn this so it's looking at me, and I'll make a couple of announcements. Where's it looking?
It's still looking at me, so you can come stand next to me.
I'm just gonna
look pretty.
I'll
stand here and look pretty.
So, fantastic presentation. Thank you so much for being here. We had a low turnout because of the tropical storm. So people want to swamp when there's a swamp to swamp in. So we'll keep that in mind. I appreciate everybody being here online. A big shout out also so next week we have AI in healthcare from let me just make sure I get the name correct here. I'm running around here. So we actually have our next 2 weeks already scheduled for one. So we have Chandra Beasley, who is a healthcare executive and head of IT, will come down and talk to us about AI in healthcare and give us some examples about what she and her outfit has been working on. So that's going to be a really exciting one. I hope everybody will come to that. And also, and I think he may be actually on the stream right now, Mike Kelly Williams will talk to us about sustainability in coding and different coding practices around sustainability on the 3rd. On the 10th. Sorry. So the 10th. We are also, and you guys can hop on the Discord always to give us your opinion. We're thinking about doing something cool for Halloween. We're floating some ideas around. I'll share some on the Discord. But if you've got some feedback on things you'd like to do on our special first Silicon Swamp Halloween extravaganza, let us know.
We can have a spooky swamp.
Spooky swamp. Spooky swamp.
It can be more spooky.
Yeah, spookier. Gosh, this guy. All right, that's it. Have a good one.
Thanks, everyone.
Now just unplug everything.
All right.